Hi, everybody. How's it going? I'm back. Sorry, we had faculty retreat on Monday. Mostly just meetings all day for 2 days, but it was fun. Anyway, so welcome back to me. I don't think I'll miss any other classes this semester unless something weird happens. So I have no other planned events. Other than the midterm 2 review, I'll be out of town for that, but that's next Friday or 2 weeks from now. All right. So reminder, for those of you who have taken extensions, office hours for a given assignment, they end 3 days after the deadline. So that means today's the last day for Project 2A office hours. You can keep asking on Piazza, but the official thing that we're doing in office hours, we're switching gears to 2B starting tomorrow. Because at that point, you're really behind, and ideally, you should get help some other way. Also, keep in mind that there exists a pseudo walkthrough that I put together. So last Thursday was a really interesting time for me where I was like, there seems to be surprisingly few submissions. This is making me nervous. Then Friday and Saturday and Sunday rolled around. So I recorded myself. I did the project about an hour and a half. I mean, it's just because I've done this for a long time. So it's not because I'm like super amazing at program and I'm genetically endowed with these powers. It's just that I've taught data structures for 8 years. So at this point, it's all in there pretty good. So I posted a subset of that. I did some unblurred, some blurred. And so basically, if you want some tips on how to approach it, I have given this away. I could have done something else weird like, this part's bonus, whatever else. But I figured it'd be better if you would actually do the thing, and then hopefully my walkthrough is useful. So any questions about this stuff? I know it's a very strange move, but I hope you liked it. Yeah. You can source however much you want to from the walkthroughs. Just put an @source tag in your comments. As I noted, you can type code that is almost the same as my timing tests and my correctness tests. That's fine. But I blurred out all the nearest code, I think. Yeah. If you just happen to implement my thing, that's fine. Yeah. The tests are very short, so it's actually quite possible. All right. Great. So I hope, though, that 2A and 2B, particularly those of you who came in with less programming background, these projects were properly particular, or continue to be perhaps, particularly difficult because it's stressing you in the exact way that the difference matters. So students who've been programming for 5 years, they're just a lot faster at this kind of like go out on your own thing because they've been doing it for so long. So don't be too disheartened if you found these projects really challenging. The goal, though, was to push you to be independent because eventually that gap should narrow. All right. So today we're going to be talking about graph traversals. We already spent a lot of time on Monday talking about them. So we're going to wrap up one more traversal called a breadth-first search, and then we'll talk about how you actually implement all this stuff. So as you know, there are lots of different tree traversals. We got pre-order, in-order, post-order, level order, and if you don't know what those things are, well, you'll have to catch up on Monday. We have also, in graphs, some equivalent orderings that we can consider our vertices in. So we have the DFS pre-order, the DFS post-order, and we ended, hopefully, on the BFS order, and we just briefly talked about it. So DFS pre-order, you could think of it as the order in which a depth-first search will make its calls. So first you call DFS on 0, then 1, then 2, then 5, then 4, then 3, then 6, then 7, then 8. And then post-order is the order in which you return. So the first one you return from is 3. The last one is 0. That's when you're all done. BFS order is whenever you visit or act on the vertices in order of distance from S. BFS is, as I think I just said, is breadth-first search. So you're going wide, a lot of breadth, rather than deep, so not depth. And so one valid BFS order is 0, 1, 2, 4, 5, 3, 6, 8, 7. You'll notice that those vertices are an increasing distance from the source, though note that, for example, 2 and 4 are equidistant, so you could actually do those in either order. So one little difference between tree traversals and graph traversals is that graph traversals are not, in general, unique, whereas tree traversals are. Okay, great. Okay, so how do we actually implement a breadth-first search? Well, I had a challenge that is in the slides, at least, at the end of the previous lecture. I will admit I have not yet watched the webcast to see if we made it that far. Did we get to this? Did you see this? Yeah, good. All right. And so maybe you had a chance to think about it, maybe not, but I'm just going to spoil it now. So the typical implementation of breadth-first search is non-recursive, and the way it works is that rather than using recursion to keep track of what you're doing, who is the active vertex, you're instead going to have a queue. And the queue is going to be a collection of all of the vertices you'd like to consider. So what is a queue? Well, if you don't know the term, It's a list that has two operations, an add last and a remove first only. We sometimes add last is known as in queue, and remove first is known as DQ. This is like you're waiting in line for a roller coaster. There's a queue, people get in at the back, and they leave from the front to get on the roller coaster, right? So that you add to the end and you remove from the front when you're done being in line. And we'll call this queue our fringe. And the reason it's called the fringe is it's the edge of what you're exploring. So fringe is just a word in English that means sort of the edge. And so what we'll do is when we run our BFS algorithm, I'm just giving to you out of nowhere, we're going to take a queue, add the starting vertex, and then mark it to say that we're done with it. Okay? I make a note here that a queue is just the opposite of a stack. Now, you don't have to use a queue. You can use an array list, or you can use a double-ended queue from Project 1A. I'm just using the simplest possible useful data structure. So then what we'll do is we'll repeat until the queue is empty. We'll take a vertex from the front of the queue, and then for every unmarked neighbor of that vertex, we'll do some stuff, and I won't explain what they are until we see a demo. Okay, so let's look at this demo. It's going to be the same code, just compressed a little bit so that it fits on a slide. And so this is similar to the depth-first paths approach you saw before. There's only one difference on the slide that you'll note cosmetically, which is that I have, once it loads, a distance 2 in addition to edge 2 and our marked array. So here's distance 2, which is going to track the total distance to a given vertex. So when we start, if our source is 0, the distance from 0 to 0 is 0. Okay, the first thing I do is the queue is presently empty, but I'm going to add my starting vertex 0 and mark 0. Okay. So now it becomes a little more interesting. So now we're going to think of this queue as everything we'd like to explore. Well, the only thing we want to explore so far is 0. So that's the fringe of our universe. So we're going to remove that vertex from the fringe. This is now the active vertex V. And then we're going to consider all of its neighbors. So vertex 1, we're going to do 3 things. We're going to mark it so that we don't explore it twice like we saw with depth first search. We're going to add, actually 4 things. We're going to add it to the fringe because we'd like to eventually explore everything beyond that vertex. We're going to set the edge 2 and the distance 2, and I think it'll be clear if I show it in this table. So I've marked vertex 1, I've added it to the queue, I've set its edge 2, which tells us how to get there, and the distance to it is 1. I'm going to do a couple more before I take questions. So next queue, on the queue, what's on the queue right now? 1. So what do? We remove it from the fringe, and I don't know why the first line's bolded, but hey. So now we've removed this from the fringe, and then what we're going to do is consider all of this vertice's neighbors. So 0 is already marked, and 2 and 4, you'll notice, are unmarked. So what do we do with those? What's going to change over here? Marked. What else? Distance 2 and edge 2. And we're also going to add it to the queue. So the 4 things that happen are marked, edge 2, distance 2, and you're put in the queue. Okay? All right. So one more. And then, so we got 2 things on the queue. Let's say 2 is at the front. So we take 2 off. Now 2 is the active vertex. How many unmarked neighbors does 2 have? 1, and that's 5. So 5, we're going to set its edge 2, its distance 2, and its marked array. So any questions about this, what I'm doing? Okay, great. So next up, who's going to come off the queue next? 4. Now here's an important point. If you look at the queue, you'll notice that it has one vertex that's distance 4 and one vertex that's distance 5. So which one, if we're trying to explore in a breadth-first manner, which one should we explore first? 4. And that's good. It's on the queue. So the queue is enforcing that rule that we're always looking at things in the order of the distance from the source. Because the queue, well, as we'll see in a moment, is always going to have the most proximal unexplored items. So 4 comes off next. It has one unexplored vertex, or unexplored neighbor, which is 3. So we add 3 to the queue. We mark it as true. We set its edge 2. We set its distance 2. And you'll notice that each time we're setting the edge 2 equal to the current active vertex, and the distance equal to the distance to the currently active vertex plus 1. Because this is basically just saying we're one step further. So 5 comes off next. It has 2 unexplored vertices, 6 and 8. They go on the queue. And so now if you look at the queue, it has a vertex number 3, which is what distance from the start. So vertex 3 is what distance from the start? 3. And 6 and 8 are 4. And so there's an invariant with breadth first search, which is that the items on the queue are always either k or k plus 1 distance from the source for some k, and that k changes over time. So at this moment in time, the Q contains vertices of distance 3 and 4. And that's really important to why this is breadth first search. You're making sure that it will work because of this invariant. Like, this is the reason that breadth first search works. Because there's no way that we're going to get a vertex of distance 5 on here. To get a vertex of distance 5, how far away would my current vertex have to be? 4. But right now, we haven't finished all the vertices with distance 3 yet, so there's no way that's going to happen. So this invariant will stay true, and therefore it will stay true. Induction. All right, any questions about that or other? Also, a lot of people here today. It's nice. Good to see you. I was a little afraid given the project. All right, so next up comes 3. 3 is removed from the vertex. Is removed from the queue. How many unmarked neighbors does it have? None, so we don't do anything. All right, who's going to be the active vertex next? 6. How many unmarked vertices does it have? 1. There we go. Doop, doop, doop. We changed those 3 things. Okay, who's next to be active vertex? 8. Nothing interesting happens. 7. Nothing interesting happens. And we're done. So that's breadth first search. Okay. Now what's cool about this is, at this point, I know the distance to all of the vertices from the source. And so if I wanted to have a method that says what is the distance, and I'd already computed this array, I could do it in constant time. I could just say, well, I know that 6 happens to be distance 4. And what's nice is that what you actually here have stored the shortest path to every single vertex, all in one array, which is pretty cool. All right. Thanks for the approving chirp, speaker. Okay. Now these steps, there's a little bit of play in here. I mean, you can decide to do this distance 2 or edge 2 thing or not. I mean, it's just a matter of whether or not, like any given implementation, you might say, is it still breadth first search if I don't do this distance 2 thing? I'd say yes. In fact, it's still breadth first search if you don't save any of this information. All that matters for it to be breadth first search is the order in which you visit the vertices. Yeah. So if you wanted pseudocode for what? For the problem. I mean, I would say, yeah, I guess if you were working with really advanced folks, you would say something like, do breadth first search where the action you take at each vertex is this, is what I would say. That would be the shortest way. If you're at a job interview, maybe you'd do that, because you probably wouldn't mention this queue thing every time. Actually, one other thing I want to show you that happens in breadth first search is that whenever you step through, if you watch which vertex is the active vertex, it kind of jumps around. So the active vertex, it will be this bolded V. So as it hops around, you'll notice that unlike depth first search, it can jump these long distances. So right now the active vertex is 5, but next it will be 3. Okay? So it's just a feature of breadth first search, and that's one of the reasons we need this other data structure to lean on. It's keeping track of this global list of all the things I need to be doing. Depth first search, as you may remember, we're always going to a neighbor. Either we're going to our immediate neighbor, or we're returning to whoever called us. Okay, so we can hop around a little. So if you just play around with it later, you can see that V hops around long distances. Okay. All right. So what good is breadth first search? Well, here's an example. So Kevin Bacon, he's a guy. He's in some movies. Here I have a clip of him in a movie. Maybe it'll play in here. Okay. No sound again. Oh, no. Grammarly. Has anybody here actually used Grammarly or just... Okay. Is it good? It's all right. Okay, cool. I've only seen like 3 million ads for it. Okay, so here's Kevin Bacon in 1984. Okay, he's teaching this guy to dance. You wouldn't think he could dance. Look at that hat. But no, he can dance. And you know who helped teach him? Kevin Bacon. All right, anyway. So what good is the breadth first search? Well, there's an old news group post. So news groups are like the Reddit of the 90s and earlier, where people were discussing this question about how far away people are from Kevin Bacon. So if you pick random people, like, let's see, I did some ones in my video earlier. We'll do Bill Murray. Okay, he's a good guy. So I find, what is the closest link between Kevin Bacon? Well, they're both in the film Wild Things. All right, someone name some famous person who's in movies. Robert Downey Jr. Okay, he's actually 2 steps away. You got to go through Avengers Infinity War to Benedict Cumberbatch to Black Mass to Kevin Bacon. All right, one more. Scarlett Johansson. No more. There we go. I don't know why I spell that so weird. Okay, same. That's weird. Okay, Benedict Cumberbatch bridges the gap again. All right. Cool. Okay, so BFS could be used if you wanted to build your own Oracle of Bacon. How it would work is you'd build a graph where each vertex is either a movie or actors, and you would alternate. So, for example, the movie Animal House, this is a figure from the optional algorithms textbook, has Donald Sutherland, John Belushi, Kevin Bacon, and other people not shown. If you wanted to find Nicole Kidman, then you would just run BFS on this graph, and you would be guaranteed to find the shortest path to Nicole Kidman, which would be presumably Animal House, Donald Sutherland, Cold Mountain, Nicole Kidman, unless there's been a change in this graph sense. Okay. So the point here is that, as we'll see in a lecture after spring break, often problems that you want to solve in the real world, or even just deeply weird mathematical problems, are really just basic problems in disguise. Okay? That's kind of fun. All right. Question for you guys. Do you think that breadth first search would be a good algorithm for, say, Google Maps? And let's say then that each vertex is an intersection, like Bancroft and Telegraph, and each edge is a road. So you'd have two vertices, Bancroft and Telegraph, and Bancroft and Dana, and you would have an edge between them. What do you think? No, why not? It would be slow? Why? Well, maybe it would be slow. What's another? Would it give you a good answer? Always. Like, what feature of the world are we missing here that might be good for driving direction? Yeah? Yeah, freeways. Yeah. Not all roads, not all intersections are the same distance apart. So some roads are longer than others between 2 points. So we'll talk about how to deal with that on Friday, but I want to talk about some really important stuff first. Okay? So we want to build graph algorithms, so we need some specific... I want to talk about how you do graphs in a programming language. So far, we've been treating it as this beautiful abstract thing, and they are, but I want to take it to the next level so we can actually build code. So to implement things like breadth-first paths or depth-first paths, we need two things. First, we need to make a decision about our API for graphs. API is a term which I never think of as actually meaning application programming interface, but I looked it up and it still means that. And so for our purposes today, that's basically the list of methods that our graph class or graph interface would have. And then we'll also include the signatures and behaviors of those methods. And that will define how you think as someone trying to work with graphs. The other thing we have to decide on is the data structure we use to represent the graphs. Is it going to be something like tree representation 1A or 2B or whatever else? So our choices, as we'll see, can have really big implications on the runtime, on the memory usage, and how hard it is to write the algorithms. So if you have an API that's either too complex or too simple, it may be that writing an algorithm like depth-first paths is hard. So I'm just going to give you, so I'm going to make one decision, and then I'm going to give you an algorithm, a graph API from the Princeton textbook, but it won't be the only choice you could possibly have. So the first thing I'm going to do to keep things simple is I'm going to say that our nodes in our graphs are always going to be numbered, kind of like we did with disjoint sets. So whereas you might have meant to make this directed graph where I have Austin, Dallas, and Houston, and who knows what these directions mean, they're just arbitrary. This is an intended graph that we'd like to build, but in our universe, we're going to say, sorry, your graphs are only of numbers, and if you want to also know who is which number correspond to which string, then we're going to have a map, or maybe a couple of maps. So here I'm basically saying if you want to know which number Austin is, you use this map. So if you wanted this graph, you're going to be stuck with using a numbered graph and a map in order to make it do the things you want. All right. So that brings me to the Princeton Graph API textbook, from the very simple API for graphs from the Princeton textbook. So they define the graph class, which is not the same thing as an abstract graph, but they define a graph class as what has the following methods and constructors. So it is a constructor where you specify the number of vertices you want, and that's fixed, and you can never change it. So you can never add node here. You can add edges between V and W. You can ask for the total number of vertices. You can ask for the total number of edges, and you can ask for an iterable, which will give you all of the neighbors of a specific vertex. They call it adj. I might have called it neighbor, or neighbors, but they call it adj. Okay? And we'll give you some practice playing around with it. So some things you might notice. You have to give the number of vertices in advance. There's no add node. It doesn't allow you to give weights on edges. So you can't say that some edge is heavier or has a certain length or whatever. It doesn't allow that. And it has no method. For example, you can't say, hey, vertex V, like vertex 6, how many edges do you have, which is sometimes known as its degree. So if this is our API, then an example of a program we might write on graphs would be this degree function here. So you give it a graph and a vertex, and it counts the number of edges on that vertex. So here, vertex 2 has degree 2, because it has 2 edges coming out of it. So how would this function look? Well, you'd create a degree variable, and then you would iterate over the iterable returned by g_v. So this is a function that returns an iterable of all the edges of 2, and then you would add 1 to your degree repeatedly, and then finally you would return that degree. Okay. That's because the iterable class, the iterable interface has no length or size method. You just have to iterate over it to know how many things it has. Okay. So that's an example of how you could write degree. So, problem for you to ponder for, I don't know, a minute just to get familiar with this thing. What would it look like to write a method that prints out all of the edges in a graph? So, for example, running your function on this would look like 1, 2, 1, 4, 2, 1, 2, 3, 3, 2, 4, 1. Okay. So I'll give you guys only maybe 45 seconds. Don't write real code. Just start trying to think what it might look like. Okay, I'm spoiling it. There's my print method. So v ranges between 0 and g.v, the total number of vertices. Then for each vertex, you have to get an iterable of all the neighbors. And if I call this v and this w, I'll print out v dash w. Okay? So that's the kind of example of a program you might write. Okay? So our choice of Graph API, it has really big big implications in terms of how you would implement depth first or breadth first paths. The fact that these are the toys or the functions or the basic building blocks you have to work with will deeply affect how you would write, for example, degree or depth first paths or whatever else. So we'll come back to that in more depth, but just be aware that an API, that's one of the hard things whenever you're programming. Learning the API to do a specific thing, and hopefully the API you're using to achieve your task is good. This would be, for example, a bad API for degree. It's like annoying that you have to write all this code to get the degree of a vertex. All right. So let's talk, before we come back to actually implementing breadth first and depth first paths, I want to go one layer of abstraction deeper and talk about how, so first we picked an API, as you guys saw. And we saw how it affected how we think about client programs. And a client is just anything that uses graph. So now we also need to decide what data structures we want to pick to represent our graphs. And whatever we pick will matter a lot. It will have a big impact on runtime and memory usage. It will not really affect, in fact, it shouldn't affect at all how hard it is to implement depth first paths or breadth first paths, because the person writing the code only has our API. They don't know about the underlying data structure. But nonetheless, our choices about how to implement our API will affect the runtime of their algorithms. So as you guys saw with trees, there's lots of different ways that we can implement these abstract objects. So trees, for example, we saw this 1A example where I want to represent to the world this specific tree, and I could do it by having a fixed number of links, 1 per child. Or I could do an array of keys, and that only works for complete trees, but we saw that it takes less memory and it should be faster, and you guys did this in 2A, hopefully. So this only works for complete trees, and both are perfectly valid choices. They do not affect how somebody thinking at this level behaves. Like, they're still thinking about it as a tree, but us, the monks manipulating reality, it's going to take us some amount of time and difficulty to implement this thing. And our choices, if you build a program that uses your project 2A to do something, like you will on homework 4, the choices you made there will affect the runtime of your homework 4. So here's the first example of a way we could represent graphs. This is the most basic possible representation. we create a gigantic array of or two-dimensional array of Booleans. And for example, here, we would say that this graph, this abstract idea, would be represented by this matrix of Booleans. I'm using 0, 1 instead of true, false for consistency with the optional textbook. So this says, for example, this 1 means that if we go from vertex 0 to vertex 1, there does exist an edge. How do I know there's no edge from 2 to 0? Well, I go to source 2 and target 0. And I see that this is a 0, meaning there exists no edge. And if you look, there are 3 edges and 3 1s. Okay? And this gives me all possible graphs if I play around with all the 0s and 1s. Okay? Now, one thing I'll note is that in this approach, an undirected graph actually has some redundancy. So this edge between 1 and 2 is represented both in this box and in this box. And you might say, isn't that redundant? Couldn't I just fill in only the top diagonal and that would be fine for an undirected graph? Sure, but this is simpler. So you get simplicity at the expense of space. Okay. Any questions about this approach? So this is one way you could build a graph, yeah. You could have an illegal graph. Yes, so if you fill in a 1 here, it's still a graph, but it's no longer a simple graph, which are the graphs we always do. But this representation will allow you to represent graphs with self-loops also, if you wanted to. But we don't in this class. So for example, to get a sense of what this would mean, this g.adge2, right? If I ask for an iterator over 2's neighbors, it gives us an iterator, and that iterator will have 2 values in it, okay? So you can call next up to 2 times. The first time you call it, you'd get 1. And the next time you called it, you'd get 3. And now, there's actually a pretty hard line on the slide. It's not obvious that this is hard, but the total time it would take to iterate over all neighbors of any vertex would be theta v. In other words, if I write a for each loop where I say, get me all the neighbors of 0, okay, I would get an iterator over this array, but actually stepping through it would take theta v time, because even though there's only 1 edge that actually exists, whatever code you use to write the iterator still needs to look at all of these entries in order to make sure that they're not 1. Okay? So in other words, g.adge2, if you iterate over it, it'll give you 1, and then 1, but the total it'll give you 1, and then 3, but the total runtime in order to do that would be theta v. That's pretty subtle, and it's something you can maybe think about a little more later. Basically, the underlying code that implements g-adge in an adjacency matrix, it has to iterate over this whole array. That's basically the proof that overall it would be theta v to look at all of your neighbors, even if you only have 1. Okay. So question for you. That print method that you guys wrote earlier, or at least just saw me do, what do you think would be its runtime? So I'll give you a little yelky here. And let's assume we're using this representation. And I have 2, jeez. Come on, guys. Okay, well, I guess I'll spoil it. And then you'll do the harder one in a sec. Damn. Anyway, I'd touched my computer in a dramatic flourish. Okay, so one way you can scaffold this is you can ask, what is the runtime to iterate over V's neighbors? So if I want to iterate over any vertices neighbors, what's its runtime? V, because I just said that. And how many vertices do we consider? V. So overall, the runtime would be v squared. You can think of it as you're iterating over this whole matrix. Okay. All right. Another example. I'll try not to mess up the other Yelke questions. So another representation you could do is just build a hash set of edge objects. And that would mean you'd have to define some edge class. I won't show it. This is a pretty atypical implementation, but it can technically do anything you want. So you would just have a set of edges, and anytime you want to say determine whether or not what the adjacent items are to a certain vertex, you just iterate over the whole hash set and find all the edges that are useful to you. Okay, I won't say much more, but I'm mentioning it just because it's a thing people use in certain special cases. But then there's the representation, as it usually goes in class. I'll show you some other ones, and I'll show you the one we will use. So this is the adjacency list approach, and it feels an awful lot like a hash table. It's not quite, though. So in this approach, what you'll do is for every vertex, you'll maintain an array. What you'll do overall is you'll maintain an array of lists. And the arrays will be indexed by vertex number. So for example, 0 has 2 neighbors, 1 and 2. 1 has 1 neighbor, 2. So this is a lot like our separate chaining hash table. It's just that rather than using a hash function and finding a bucket, it's just that we have 1 bucket per node. Okay? And this is the most popular way that graphs are represented in practice, for the reason that graphs are typically sparse. And I'll tell you what that means. Okay? All right. So question for you. What is the order of growth of the runtime of print if we use adjacency lists instead? Okay? And let's say V is the number of vertices and E is the total number of edges. So E is not the number of edges per vertex. It's the total number. So here E is 3. Okay? So I've given you some scaffolded questions you can ponder. Good luck. Let me give you a hint in a sec. You can lock in a vote now if you want before I give you the hint. Okay, here comes my hint, even if you haven't answered yet. Okay, so the runtime, I haven't given you the answer. I'm just pointing out some things. So the runtime to iterate over V's neighbors could actually be now variable. It could be anywhere between 1 and V. So if the list is short, then it will be, all the lists are short, they'd be constant time. But certainly it's never going to be more than V, because each list can have no more than V items. And we have to consider V vertices. So the best case is theta V, that is, all the lists are short or empty even. And the worst case is theta V squared, where all the lists are long. Okay, let's try again. Okay, I changed the Yelke link, by the way, if you want to answer again. This is a hard runtime question. Okay, I'm going to spoil it. So I just wanted you to hit this. It's actually a pretty challenging runtime problem. So the correct answer is V plus E. And it turns out that's a very common runtime in graph algorithms. Now, usually it's going to be big O of V plus E. But in this case, I can make a theta bound. Okay, so here's kind of the basic picture here, which is that we're going to create V iterators, all right? And we're going to print E times. The number of different lines that gets printed out is E. And so overall, our runtime will be V plus E. Okay. So another way of thinking about it, this is like a way to interpret this funny function of theta V plus E. All right. So remember that asymptotic growth works like this. You're increasing V and E over and over and over forever, and you want to know how much things will grow. Now, there's different possible cases. So let's take an example. Let's say we're increasing our graph, and we're building this funny mathematical construction where E is growing really slowly as the number of vertices increases. So let's say that we're building increasingly large graphs, and every vertex is simply connected to its square. So 2 is connected to 4, 3 is connected to 9, 4 is connected to 16, 5 is connected to 25, and so forth. You can show, but I will not, that the number of edges in such a graph is just because of the bizarre mathematical construction that I just made up, will be theta square root V. So the overall runtime will be the time needed to create all those iterators, plus the time needed to print out all those edges. And so V plus square root V, in this case, V is bigger. So we can just simplify it as theta V. That's the best case. The other example is, let's say, on the other extreme, we have a very dense graph where every vertex is connected to every other. So in that case, the number of edges is V squared. And so the overall runtime would be V time to create all of the iterators. And it would be V squared time to actually iterate over all the lines. Now this is I would say this is a very challenging runtime problem. The good news is that when we do depth first search and breadth first search, we're not going to have theta v plus e. So this I'd say is a very, very hard runtime problem. I'm going to keep going, though. And if you have questions, you can ask me later. All right. Okay. So to get some idea of how our choice of representation affects our lives, let's say we want to add an edge. I mean, I didn't build this table. So adding an edge is theta one time in all of the representations. However, for example, printing is not. So for printing, if you use an adjacency matrix, I spoiled that one and said it's theta v squared. If you're using an adjacency list, it would be theta v plus e. Printing, the whole, for a list of edges, would be theta e, because you're just iterating over your set of edges. We didn't really talk about this one much. And for example, if I wanted to know, does there exist an edge from S to T? Well, then we would say in an adjacency matrix, it's very fast. I just look at the entry in the two-dimensional array. In an adjacency list, I have to look through that whole list. So it'll be whatever the degree of V is. I do not expect you to memorize this table. I'm just throwing it up there so you can explore this later. So maybe one good challenge for you is to see if all of these entries make sense to you. And the hardest one to understand is definitely the one we just did. Again, having spent 5 minutes on it and me explaining it, I still expect it to be pretty hard. Okay? Now, I want to mention the only really important point on this slide is that in practice, adjacency lists are what people use. And the reason is that most graphs are sparse, meaning that each bucket, each node doesn't have many edges connected to it. All right, any questions other than details of this proof? Yeah. Yeah, good point. Okay, so the reason is that in a list of edges operation, so here, let's see, what do I want to do? So printing, yes, but getting the adjacent, this is why, actually. So if I want to iterate over the edges of a particular vertex, each one of these loops would cost theta e time. That's why. So if I want to get, for example, all of the edges that are adjacent to A, I have to iterate through every single edge in the entire list. Okay. Other question? Yeah. Correct. Yeah, okay. So the question was, does it ever make sense to have two representations and use one for certain fast operations, for operations to be fast, and a different data structure for other operations when you need them to be fast? Yes, though I don't think we see any examples in this class. The cost that you have in that case is needing to maintain two parallel copies. There's probably cases where it's helpful, and I bet in databases it happens. So when I teach W186, maybe I'll learn. I don't know. Yeah. Other question? Okay. Cool. What would it actually look like in code? Well, this is the graph implementation that Princeton provides, but I made it a little less weird. So we have in the constructor, we set v equal to whatever the v is that was passed in. We create a list of, or an array of integers, an array of lists of integers. And then after we've created this is basically declaring the variable. No. This is creating the array, and this is creating each of the lists. Okay. Adding an edge is pretty simple. So this is an undirected graph. So we need to make we need to make sure that the edge is in both of the two bins for an undirected graph. So this is just that redundancy thing, that an edge from 0 to 1 is represented twice. And then the adjacency method that gives us all of our neighbors just returns the list. However, it is cast as an iterable instead of a list. Why did Princeton do this? I don't know. I would have said list here, but they said iterable. All right. Cool. Okay. So now let's talk about how our traversals will actually be implemented, and hopefully we'll talk about runtime as well. We'll see. So first thing I should let you know is that when you actually implement these algorithms, it is a very common pattern that you'll decouple the type, the actual, say, the graph type, from the processing algorithm. So often what you'll do is you'll create a graph object, and then you'll pass that object to some other class. So it's not that you're going to create a depth-first paths method inside your graph class. Instead, you'll take, for example, you'll have a paths class that it will accept a graph. It'll take the graph in, and then it will think carefully. So here's the graph object, or the paths object. You give it a graph, it carefully thinks about all the things that could possibly happen in this graph, it sets up all those arrays, and then once it has done so, then it can return back has path 2 or path 2 in a rapid amount of time. Okay? So for example, this is what some pseudocode might look like. We say paths p equals new paths, graph comma 0. So this object here, this paths object says, okay, vertex 0. Okay, I figured out the answers to everything. And then if you then ask the paths object, hey, why is paths object? Is there a path to 3? It will say true. Or if you ask why is paths object, what's the path to 3? It will return 0, 1, 4, 3 rapidly. And in the constructor is where you're going to do all the work. It's kind of like in Project 2B when you build a KD tree. You do all this work up front in the constructor so that other work is fast later. Okay? So let's review how depth first paths works really fast, just to remind ourselves of what this thing was so we're not coming in totally cold. So if we wanted to implement this demo from last time, I'm just going to race through it just to get the texture. So when depth first paths begins, we hand it the graph, and we say, I'd like you to think upon this graph starting from vertex 0. And so the constructor will go through and make all these calls, okay, does all that stuff. And once done, we'll have created this marked array and this edge 2 array. So this is the result of the paths object's deep meditations on the graph. It has all of this information available. Okay. So implementation then. Let's see. Are we running out of power? Hopefully not. We got 20%. Plenty. Okay, good. So this is what the depth first paths implementation might look like. And I don't care that you look at this code super deeply. In homework 4, you'll have a chance to build graph code. You can come back to this kind of thing later. But basically, depth first paths has 3 instance variables. It has a source that's just handy for it to keep in mind, though you don't really have to keep that one around if you don't want to. You have an edge 2 array that stores the actual paths, and then you have marked, which says whether or not something was reached. So when you start, you create these objects. I didn't show that. And then you just call depth first search on the graph starting at the source. And then what depth first search does in this case is it marks each vertex. Then for every unmarked neighbor, it sets the edge 2 and it calls DFS. There's no distance to in this case. Okay? That's the basic approach. So question, once this paths object, or in this case depth first paths object, has pre-processed a graph, how would you write hasPath to? What do you do? Which of these instance variables is useful? What do you think? So I want to know, is there a path to 6? What do you do? Well, you could check edge 2, maybe. There's actually a better answer, though. Marked. So if 6 is marked, you know that there's a path. Okay, so hasPath to is real easy. You just return marked v. How about path 2? Well, there you have to do a little more work. You have to say vertex 5, where'd you come from? 3, where'd you come from? 1, where'd you come from? 0. So here's some code. Not going to go over it. Okay. So here's my other really hard runtime question that I'd like you to think about. So give me a big O bound for the runtime for this constructor. Or, yes. Yeah, this is the constructor. What would it be? Good luck. I don't know. I probably couldn't do this if I was in your shoes, but I want you to think about it a little. And let's assume your graph uses an adjacency list. So the first thing you might try and figure out is what's your cost model? Okay, I don't feel bad at all spoiling this, because if you come back and do this again tomorrow, I don't know if you'll get it. All right. So the correct answer turns out to be V plus E. Okay, so that came up again, big O in this case. And the cost model in this case, this is actually pretty tricky. So if you only picked the number of times that you did this, or if you only picked marked, let's say you used the number of marked as your cost model, where would that not work? It's kind of tricky. So that would not work if there was a graph with no edges, because then your runtime would say 0. But that's not true, because the runtime also depends on the number of vertices. So you can't just count marked calls. You also can't just count calls to this, though, because you also need to take into account the number of edges. So if you only look at the number of vertices you consider, that's not good enough either. So in total, you need to take into account both the number of vertex visits and the number of edge considerations. So while it may seem daunting, one thing you could do if you wanted to try and get an intuition for this is you can just go through this demo and think about how many times each vertex and edge is considered. So basically, each vertex gets to be the active vertex once. I mean, there's some backtracking, but everybody gets to be considered once, and each edge gets used twice. So for example, why does this edge get used twice? Well, because 1 looks at 4 and 4 looks at 1. And so it's kind of a counting game. But this is a pretty subtle piece of analysis that takes some time to really grok. Okay? So overall, the argument, there's many different ways to come at this. But one is each vertex visited at most once. And what I mean by visited is it gets to be the active vertex. Each vertex gets to be V one time. And each edge is considered at most twice. Okay? The reason I say at most is some edges may not be used because they're not reachable from the source. Okay? And so overall, the runtime is V plus E. This is a hard runtime. Okay? But we'll hammer it into you in discussion. All right. So overall, then, depth first paths, its runtime is big O of V plus E, and the space is theta V because we need this array of edge 2 and marked arrays, or values. How about breadth first paths? So I don't really care about reading this code in any detail. Looks like that. You can look at it later, but there's really not much to it. Okay, it's like, it does a lot to it because you're looking at the slide and there's tons and tons of symbols, but this is almost a direct translation of our pseudocode. Okay. Now it turns out that the runtime for shortest paths, for breadth first paths, is the exact same thing. Its constructor is also V plus E, and in this case, it's the same cost model. You're counting the number of next calls, basically, inside this. It's almost the same, I should say. So you're counting the number of next calls here and marked checks. Okay, so it's a very, very similar idea. And if you understand this, which I do not expect you to at this moment, but if you understand this, breadth first paths is very close. Yeah. So BFS is superior in the sense that it gives you a shorter path. Are you saying in terms of runtimes, or? Oh, I see. Yes. Depth first paths. Why would you want this? I have no idea. Yeah. One reason is maybe it'll terminate more quickly if you're just trying to find any path at all. But yeah. I would say depth first paths is more of a toy program for lecture purposes. All right. So, wrapping up. I would like to point out an important fact, which is that abstraction happens, of course, in layers. And if these runtimes are hard. I don't really expect you to be able to get them in the middle of lecture, but I do want you to take this lesson home, which is that the choice of graph API that we make has really important implications on what programs look like that do graph stuff. So if I want to write depth first paths or breadth first paths, it will depend, obviously, on what methods graphs provide. That's like kind of duh. However, it is also the case that the choice of how to implement the graph API, so whether we use an adjacency list or an adjacency matrix, is going to very profoundly matter. Like if I change from an adjacency list to an adjacency matrix, our depth first paths runtime will no longer be V plus E. And so an exercise for you, I didn't think I'd have time in here today, but an exercise for you is to try and figure out what is the runtime, and I'll spoil it because that way you have some goal. So it turns out the runtime, if you use the exact same algorithm, depth first paths, just with this as the underlying representation, it'll be V squared. Okay? So try again a little later. And so ultimately, if we use an adjacency matrix, BFS and DFS are V squared, and if the graph doesn't have many edges, that's really bad. So we're going to use adjacency lists generally. So to summarize, before we go, sorry, we're kind of going quickly here. So we basically we saw BFS as our new algorithm, and we made two important choices. The first was graph API, and I showed you the Princeton API, but there are lots of other possible ways to represent graphs than this. You'll get your own choices when it comes to homework 4. And again, the methods that are available will really matter. And then we saw implementations. There's 3 different ones we saw. We're always going to use adjacency lists. And my homework for you that you should think about over spring break or in discussion section once we get back is really trying to deeply understand these runtimes for adjacency lists and matrices. So on Friday, for those of you who are here, hopefully I'll be here, we'll be talking about shortest paths, and that's what you'll need for homework 4. All right. Good luck on the project if you're still doing it. Have a good spring break if you're not here on Friday. Bye. Aw, thanks, guys.